Thank you, Nadia. So, good afternoon, everyone. So, today I just wanted to give a high-level overview of different types of advanced chip packaging, and also kind of give a snippet of, let's say, like a few case studies. So, okay, so. So I'll be talking about the different types of advanced packaging, and also, let's say, like what are the process models used in these advanced chip packaging. And my case studies will cover on photonics, quantum, and RF, and I will conclude with an outlook. Okay. And if you look at the, let's say, like the packaging landscape, so previously with the traditional packaging, we were mainly focusing on wire bond and flip chip. But the advanced packaging started to evolve when, let's say, like when the cost of economic scalability of silicon diminished, so people started looking into like various packaging capabilities to, let's say, like have high integration density and reduce the interconnection distances between the chips. So that's where, let's say, like a lot of foundries started looking into the advanced packaging, and that can be broadly classified into wafer level packaging, 2.5D and 3D. And if you look into, let's say, like the bottom part of this slide, so you can see that various foundries work on different type of advanced packaging. They have their own version of, let's say, like the interposer or the fan out, but they also kind of involve in all these types of packaging. So they're not just limited to one type of packaging. So this kind of says that, okay, maybe that is not something like a one size fits all, so. And one of the key things that drives this advanced packaging, as I said earlier, is the interconnection distance between the chips. So if you kind of take a closer look at the interconnection technique for these different types of advanced packaging, so for example, with the 2.5D, for the 2.5D, you could see basically the silicon interposer technology, the organic-based interposer, and the glass-based interposer. So the interposer technology predominantly dominates the 2.5D. And for the 3D, it's mainly the hybrid bonding and the microbump process, So in my talk, I've tried to focus mainly on the silicon-based interposer. So where I will go through silicon via as well as the silicon bridge. And then I will also talk a bit on the hybrid bonding before diving into the case studies. So for the interconnect process itself, so the silicon interposer, so basically it utilizes the standard functional blocks of a semiconductor process. So you start with, let's say, like a deep reactive ion etching process to define the through silicon via, and then you also go through the standard copper plating, CMP process, and then in order to connect the dies to the interposer, you use a micro bump, and then for the interposer to the package, it's mainly, let's say, like the solder bumping process. And here I have kind of given a typical example of aspect ratio of TSV, which is like 1:10, and the micro bump, which is about 40 micrometers, and the die-to-die spacing is about 100 micrometers. And of course, this will vary depending on the foundry capabilities and also the application types. But these are, let's say, like some of the limits of the silicon interposer process technology. And it is quite interesting to note that one of the first commercial products of this silicon interposer was Xilinx FPGA in 2012. So it's been existing for quite a long time now, the silicon interposer technology. Then moving on with the silicon bridge, as I mentioned earlier, for the 2.5D integration. So here I wanted to share the embedded multi-die interconnect bridge process from Intel. So what basically they have done is that they have kind of embedded, let's say, like a kind of a silicon bridge over here within an organic substrate. So the advantage of using such a silicon bridge process instead of TSV is that you no need to do all those through silicon via etching and other additional processes related to that. And also, there is also no need for any kind of a backside surface process as well. So this kind of simplifies the advanced packaging of 2.5D process, and also thereby increasing the throughput and also reducing the cost as well. And typically, I think this EMIB process is heavily used by Intel in the AI sector, and also even IBM is looking into the silicon-rich process for their, let's say, for the latest devices. And then moving on for the 3D packaging technology. So I wanted to share something about hybrid wafer bonding. One of the key limitations with respect to the silicon interposer technology is that as I mentioned earlier, so the bump pitch is about 40 micrometers. But if you wanted to go for like a more, let's say like a more integrated connections, then you needed to have like a pitch below 10 micrometers, and that can be achieved using hybrid wafer bonding. The reason they can do that is by just doing like a copper interconnection instead of the bump, and that's where the hybrid wafer bonding is getting more traction nowadays, and it is also used in various applications such as CMOS image sensors, memory, as well as 3D system on chip. Moving on to the case studies, the first one I wanted to share here is the photonics. So with respect to the photonics, what happens is that, so this one is a research paper from A-Star in Singapore. So they have done a 3D silicon photonics packaging using TSV. The reason for approaching this 3D silicon photonics packaging is that they wanted to have like overcome all the difficulties in the integration of EDA tools, processing skills, and also, needless to say, the footprint of the CMOS chip as well as the photonic blocks are quite different. So that makes it all challenging when you wanted to do the, let's say, like a kind of a monolithic integration. And it's here with respect to the 3D silicon photonics, so they have done a through silicon via along with the waveguide array and Mach-Zehnder modulator along with the germanium photodiode. So, and the main reason, or let's say like the main outcome of this work was that they were able to get a high-speed communication routing with a low power dissipation, and also they believe this is one of the promising solutions for scaling of terascale communication systems. And the next one I wanted to kind of share is the quantum one. And with respect to the quantum, so the fault-tolerant quantum computer architecture is quite challenging. It demands integrating of several qubits with optimized signal routing while maintaining the quantum coherence. So this work from University of Southern California. So they have, let's say, kind of heterogeneously integrated electrical and optical quantum components with, let's say, like a high fidelity directional quantum links using through silicon via, as you can see here in the bottom right picture. And they have also utilized hybrid wafer bonding techniques to do the transducer chip integration, which is on a sapphire substrate to the silicon interposer technology. And my final case study is based on an RF application. So this work from Leti in France, they have utilized a high resistive silicon interposer for their, let's say, like a commercial radio technology. So they have 3 different CMOS chips, one for the modulator, one for the video graphics, the phase lock loop, and then along with that they have the power amplifier, everything integrated in the SOI-based silicon interposer on a high resistive substrate. And here you could see the cross sections of such a interposer along with your RDL layers and the underpump metal process. And one of the key outcomes from this research paper is that so they were able to shrink the footprint of the device by 60% going via this heterogeneous integration technology. So this kind of gives an overview of like what sort of advantages you can achieve by using advanced chip packaging. And finally, I wanted to kind of share some outlook on how this advanced chip packaging technology is evolving. So this was a recent study from NOMAD about the evolution of patent publications in the advanced semiconductor packaging technology. And as you could see, by 2023, there is a significant rise in the hybrid bonding technology because you can achieve much below 10 micrometer pitch. And then there is also a lot of interest or a lot of patent activities in the fan-out packaging, which our guest speaker will be talking about. And then And then with respect to the interposer, there's been still activity going on. And with the bridge, it is slightly lower because it's mainly focused on few players, mainly Intel and IBM. And so that comes to my final slide. So I think the take-home message, what I wanted to deliver here is that heterogeneous integration enables scaling. There are multiple variables to consider when you wanted to have advanced semiconductor packaging, and then you might need to combine silicon interposer with a hybrid bonding or a fan-out with a silicon interposer. So there isn't like one size which can be used for all kind of applications. And then, of course, the essential factors are the pad pitch, the line spacing, and the layer counts, but there are also challenges with respect to the reliability, the wattage, cost, and the yield, and so on. So everything has to be tailored according to the applications. And then last but not least, the collaboration is the key. So AMRF provides the facilities to develop these technologies, but as Nadia mentioned earlier, it all starts from the chip design, and we need to take into account how it kind of translates into, let's say, like for the PCB packaging and the final testing. So I think this collaborated effort will be the key to bring this advanced semiconductor chip packaging success in Australia. Yeah, thank you very much.